Welcome. After learning the basics of the various processes involved in the natural gas processing like heat transfer, fluid mechanics, mass transfer, etc., now we shall go to the actual processes, and one of them is dehydration. This particular lecture will be devoted to dehydration of natural gas, and in this particular lecture we shall be learning about the need for gas dehydration and the natural gas dehydration methods like absorption, adsorption, direct cooling, membrane separation, and use of calcium chloride. So, these are some representative methods to dehydrate the natural gas. So, first let us see that why do we need to dehydrate natural gas. There are some various reasons for that. One may be that we want to avoid the formation of the gas hydrates which are formed when water kind of adsorbs or water captures some kind of gases like methane, ethane, etc., or carbon dioxide present in the natural gas, and it will form some kind of solid which looks like ice. So, these hydrates, when they formed, they can choke the plug valves, fittings, and pipelines, and water can also react with the acid gases like H2S, CO2, etc., and can corrode the various pipelines and the equipment. Then water itself can freeze and form ice, and this ice can cause erosion and corrosion of the pipelines, and if we are carrying out some kind of cryogenic processes like during the liquefaction of natural gas, these will be difficult to carry out in the presence of water, because water will freeze and will choke the pipelines. And presence of water vapor also increases the volume of the natural gas and also reduces the calorific value or the heating value of the natural gas. So, these are some of the reasons for which we need to dehydrate or remove water from the natural gas. Here are some common methods which are used for the dehydration: absorption, adsorption, direct cooling or refrigeration, and we have some less common methods are being developed, that is membrane permeation and use of calcium chloride. These methods, membrane permeation is also being researched upon and it is also being developed, but for the time being we are more concerned with the absorption, adsorption, direct cooling. So, let us see one by one each of these processes. So, in absorption, what we do, that it is very common process, and it is the water is removed by absorbing in some kind of a solvent, and the solvents used in this industry are glycols, and we have monoethylene glycol, diethylene glycol, triethylene glycol, and tetraethylene glycol. These are some of the commonly used solvents to remove water, and among these triethylene glycol, or which we call TEG, is most common. And why? Because among all the glycols, it is easier to regenerate this glycol. These glycols are regenerated by passing steam over them. So, it is easy to regenerate this TEG, and we can get only about 98 to 99% of the TEG after regeneration. And it has higher theoretical decomposition temperature. We want that the solvent should not decompose at high temperatures. So, TEG has very high temperature for its decomposition, that is, it is quite stable, and then it has low vaporization losses. It means it will not vaporize easily into natural gas, thereby it will reduce the chances of contamination of the natural gas by itself, and it has quite low capital and the operating costs. And here is a typical representation of absorption of water by TEG. Here we find the wet gas means natural gas with water is coming through a scrubber. In the scrubber we are removing all the particulate matters, and then it goes to this column which we call demister. In this we are contacting this with the TEG. We call it lean TEG. Lean means it has less amount of water, and then it goes down and this gas moves up due to buoyancy, and then what happens at the bottom, we are getting rich TEG. Rich TEG means it is now having lots of water with it, and this is again flashed, and we learned about flash earlier. So, we can see that applications of various types of process and fundamentals which we learned earlier in this various processing of the natural gas. So, we did flash calculation earlier. So, here we find that by flash the hydrocarbon vapors are taken out and we get this rich TEG further, and then it is passed through some exchanger, and here we are passing it to some oil to get back the TEG, and ultimately we are putting the lean TEG and again putting it back to the column, whereas this gas goes out of the column with reduced amount of water and we call it dehydrated gas. So, this is the overall representation of the dehydration process. And the advantages of this absorptive dehydration process are that it has low equipment cost, it offers less pressure drop, and that pressure drop translates into the pumping cost. So, we are reducing the pumping cost also, and it is a continuous operation. That means, we do not need to make up the loss because we are not losing much of the TEG, we are able to recover almost 98 to 99% of TEG. So, we do not need to put too much of makeup TEG in the system or the solvent in the system, and we have little problem in recharging of the tower, and it can handle fouling by causing materials like which pose problem in the adsorptive dehydration. So, we are reducing the chances of fouling, but it has some disadvantages also, like the glycol solutions may get contaminated by some suspended matters like iron oxides, that is by rusting. If there is some rusting, the iron oxide will come from there, the scale formation, dirt, etc. They can contaminate the glycols. Then there could be sludge formation when the glycols get overheated, and these sludges will get collected on the surfaces of the various equipment, and they may also cause some kind of stoppage of the flow, and also they will reduce the proper contact between the solvent and the gas. So, that way they will reduce the efficiency of dehydration. Then they may form some corrosion products by reacting with oxygen and hydrogen sulfide. Then they need some separation unit to remove hydrocarbons, water and lubricating oil from natural gas, otherwise these will react with the glycols. It can cause foaming, and when there is lots of foam, what will happen, that they will carry over the liquid, the gas will be carrying over the liquid along with it. So, will loss of this material and increase in the viscosity or even freezing of glycol at lower temperatures. That means that glycol may freeze at lower temperatures. Now, we go to the another thing at the adsorption. In the adsorption, we have the various types of adsorbents which are used like molecular sieve, silica gel, alumina, etc. And these are the factors in this. It is affected by the oxygen and how oxygen can react with the methane to form water and carbon dioxide, and this is an exothermic reaction which causes the overheating of the bed above the design temperature. And if there is overheating, then what happens, that instead of adsorption, the solids will get dissolved. That means we will not be able to achieve the desired dehydration due to this overheating of the bed. Then the hydrocarbon binders which are there in the molecular sieve get partially oxidized in the presence of oxygen. So, we have to make sure there is no oxygen in the system, and once this molecular sieve get partially oxidized, what we will find that they will form alcohol and carboxylic acid, which will turn into water and carbon dioxide. And then this oxygen can also convert the H2S into elemental sulfur, sulfur dioxide and water, and then it can produce olefins that can form coke and deposit in the bed, and if they deposit on the bed, what will happen, they will choke the bed and thereby they will reduce the capacity of adsorption. Water will also generate water vapor when it reacts with the other hydrocarbons, and this will cause a reduction in the water removal capacity by generating extra water due to the reactions. and it can form some kind of carbonyl sulfide, which will increasing the regeneration time and the amount of regeneration gas to be used for regeneration, and this will increase the cost of compression of the gas. And the bed temperature should be kept between these two temperatures 150 and 190 degree centigrade to avoid any kind of reaction with this carbonyl sulfide. And here it is a typical adsorption system for dehydration. Here we find we are having two adsorbers. Here we have the wet feed gas which is coming through some inlet separator, and one of these beds will be undergoing adsorption and the other one will go for regeneration. That means we can say that the wet gas comes, suppose it comes to the first bed and then it goes out, dehydrated gas, and these black ones represent the valve is closed. So, initially we find when it goes from here, this valve is closed. So, this particular bed is under regeneration. So, once this particular bed gets saturated, then this valve gets closed and this valve opens. So, now the gas will go and it will come from this bed. So, this is the way that alternately these two beds are undergoing either adsorption or regeneration, and then we have the compressor and the cooler to compress the gas, and this is how we are able to get the dehydrated gas from the adsorption system. Now, let us look into the advantages of the adsorptive dehydration. We find that they have lower dew point, and we learned that dew point is a representation of the water content of the natural gas. So, lower the dew point means we have less amount of water. So, they can give a better dehydration for the natural gas, and they are less affected by changes in the flow rate, pressure and temperature, and they are less susceptible to corrosion or foaming, and which was the case with the solvents. The solvents can foam, but this is not foaming, and they are best suited for large volumes of gas under high pressure. They have higher contact temperatures, may be tolerated with some adsorbent without getting destruction of the adsorbents. That means destruction means in terms of their chemical nature or physical. So, they cannot get destroyed by higher temperature. Some of them can withstand the high temperature, and they have high tolerance to sudden load changes, especially during startup. If there is a change in the flow rate of the feed natural gas, they can still sustain the operation without sacrificing their performance. They can get quickly started up after shutdown, and they have high adaptability to some hydrocarbons in addition to dehydration functions. They have some disadvantages also, like their capital cost are high. They also result in higher pressure drop. They can get contaminated by heavy hydrocarbons like H2S and non-hydrocarbons like H2SCO2, and they can undergo mechanical braking due to the attrition. They need high space for their accommodation, and that is how they increase the weight of the system, and then they have high regeneration requirement for, and that means the heat requirement or the energy requirement for the regeneration is higher for these adsorbents. Now, we come to the direct cooling or refrigeration. In this case, what we find that there is a Joule-Thomson effect. The Joule-Thomson effect is an effect which is found when we pass some gas through a valve, and what we find that on expansion on the downstream of the valve, there can be a reduction in the temperature of the gas, and this particular effect is called Joule-Thomson effect after the name of the two scientists who invented this particular phenomenon. So, this Joule-Thomson effect is the basis of cooling the natural gas, and when this effect happens, that the temperature is lowered, and that is how the water vapor can get condensed out from the natural gas. But in this case, what could happen, that gas hydrates may get formed, and as we learned that gas hydrate formation will be having a bad effect on the process, because they will choke the system, and to reduce the formation of the gas hydrate, what we can do, that we can inject some of the glycols which we are using for absorbing water, and so that these gas hydrates get destabilized, so they will not be formed. And other way is that we externally heat the system to destroy these hydrates. So these are the things we have to do if we find there is too much of cooling and water is going towards solidification. And by this low temperature dehydration, we can remove both the water and the natural gas liquids, that is NGL, about which we shall learn later on. And this is economical when natural gas temperature is very high, and it is recommended for sweet gas with a wellhead pressure considerably greater than pipeline, because when the pressure is very high, then on this Joule-Thomson expansion we get higher cooling. So a high pressure is desirable on the upstream of the Joule-Thomson valve. So in that way we find that if the initial pressure of the natural gas is high, then this works very efficiently. And this is often used not with alone, but in conjunction with the other dehydration processes, like with solvents or adsorption, we use this low temperature method. Now here we have the process description. What we first do, we throttle the wet natural gas in 2 steps, and when we do it with this Joule-Thomson valve, it causes partial condensation of water vapor, and the droplets are removed by demister inside the flash tank, and then we use some air pre-cooler and some external cooler. If there we find that the pressure difference is insufficient to cause enough cooling of the by jetty valve. And when we are using this pre-cooler or external cooler to compensate for the reduced cooling by the jetty valve, what we are essentially doing, we are increasing the operating cost of the processing. So for if the usable pressure difference is large, then jetty causes. That means, as I told you, that if we have a very large pressure difference between the inlet and outlet of the jetty valve, we will find there will be enormous amount of cooling, and that cooling may result in hydrate formation. So whenever we are operating such plants, we have to see to it that the delta P, that is the pressure difference across the valve, is not too small or it is not too high. So too small will be needing some pre-cooling, and if it is too high, it may lead to the hydrate formation. So these are the ways we have to optimally choose the operating conditions and the other equipment. And external heating will be needed if there is any kind of hydrate formation or the formation of the ice. So here is the representation of this whole process. The wet gas comes, and it is there is jetty valve over here, and this jetty valve, then it causes the condensate will come out, and then it is flashed over here. It goes again through a cooler, and again it goes to another one, and here we find that we are putting a glycol. As we said, that it works well with conjunction with another system, like in this case we are doing absorption. So this glycol is put to again dehydrate this thing, and this thing is done in 2 steps to remove the condensate, that is basically water, from the natural gas, and ultimately we get the dried gas from this second column. Now the advantages and disadvantages are like this, that in the advantages, this low temperature dehydration can meet water and hydrocarbon specifications for pipeline gases when we have enough or high enough wellhead pressure available, and their operating cost is low if we have the naturally occurring pressure, and the corrosion problem is also minimal, especially when the hydrates are not formed. But their disadvantages are that they are less efficient, as they cannot lower the dew point of the water for pipeline transfer, and if they cannot lower the dew point, it means they will not be they are not removing enough water from the natural gas, and they are unattractive when we do not have enough wellhead pressure. That means we try to utilize the wellhead pressure to drive this particular type of process without the use of any kind of compressors, and we have to use some hydrate inhibitors and some external refrigeration, and these will, what will happen, they will be increasing the capital cost and the operating cost. That means to remove water, again we are adding another chemical which is in a way is also increasing the processing cost of the natural gas. Then we have the other methods like membrane permeation. In the membrane permeation, what we are doing that we are having this feed gas which is pre-treated to remove any kind of particulate matters, then it is heated and then it pass through some membrane. And what are membranes? As we learned that membranes are some semi-permeable barrier. So, they will retain some of these solutes and some of them will be passing through the membrane. So, we find that through the membrane these H2O, CO2, H2S they are passing through. That means the gas which is retained on the membrane will be almost a dry gas. So, this is how the membrane is working for dehydration. And the preferred operating conditions are like this, that inlet gas must be at least 10 degrees centigrade above the dew point of water. Otherwise, what will happen? This water will get condensed and they will settle over the membrane surface and they will not allow further separation. And the feed should be taken at a very high pressure with a very low contaminant, because high pressure is needed for driving the particular solute through the membrane, and these are generally preferred for offshore and for remote site applications. And it is generally done near the wellhead, because near the wellhead there will be quite high pressure, and also we can the temperature is high enough that it will avoid the formation of the hydrates and also corrosion in the gathering system. So, hydrate formation and the corrosion will be reduced if you do it near the wellhead due to the high temperature. And these are some of the membranes used. These are basically some hydrocarbon based materials, the Pebax, which is basically a thermoplastic elastomer made from polyamide and polyether, and we have another sulfonated polyether ether ketone, and that is known more as SPEAK. And here are some advantages of the membranes, that they are a modular construction, that means, and they have less weight. Modular construction means they are coming in small units, and the advantage is this: depending on the demand, we can either reduce or increase the number of modules for operation. So, all the modules need not be run together. So, this is the advantage, and then they have very large turn down ratio, which means that the ratio between the maximum and minimum capacity is quite large. That means that they can handle large fluctuations of the feed flow, and they have low maintenance and low operating cost. The disadvantages of the membrane process are that they are quite complex, they consume high energy, and their operating costs are large, because they need multiple stages and sometimes recycling, and they are very prone to some mechanical and thermal damage due to high pressure and high temperature. Some amount of methane is lost into the water vapor permeating through the membrane. That means we are losing some of the methane which is present in the natural gas by permeation through the membrane, which is not desirable, and that makes membrane non-competitive with absorption, because in case of absorption no methane is dissolved in the solvent. So, that way membrane is not very good in comparison to the absorption process, and these membranes need some feed pre-treatment. Otherwise, what will happen, any kind of particulate matters that are there in the natural gas will choke the membrane pores, and it will reduce the efficiency of separation through the membrane modules. Then lastly, we have the calcium chloride. In this calcium chloride, it is not much used now. This is based on basically adsorption, and what happens that it is used for only small capacity, about 2.5 million standard cubic feet per day, where we need very low dew point, and but it is not very good for high capacity, even though it can give us a very good dehydration. What we find that the wet gas is contacted countercurrently with a downward flowing concentrated calcium chloride brine solution. That means the wet gas moves up and the brine solution which comes from the top to bottom, and they get contacted countercurrently, and it is found that about 1 kg of calcium chloride is needed to remove about 3.5 kgs of H2O. Its advantages are that it can operate unattended when we use a fresh calcium chloride. It has no fire hazard, it is quite compact, and it has low capital cost. On the other hand, the dew point limits the use of this water calcium chloride, because all these things are the dictated by equilibrium. So, the dew point is one consideration which is there, which can lead to this equilibrium between the water and the calcium chloride. And these are the various references to know detail about these processes. Thank you.